This is video 4.21, and we are in section 4.8 of the text entitled The Rich Variety of Factor Analysis Models. The next several pages in the text talk about the different kinds of factor analyses, whether it's principal components, exploratory factor analysis, or confirmatory factor analysis. And I have created a table here in which I've summarized all of these. If you look here at the top one, when we're looking at the factor analysis method, we first have principal components. I want to talk about what the characteristics are of principal components analysis and then compare that to the other analyses that are talked about in the text. Principal components, or PCA, uses correlation or covariance matrix with ones on the diagonals of that matrix. It uses all the possible variants, and components are linear functions derived from the observed variables. Now contrast this with exploratory factor analysis, which I have highlighted in yellow, and you see in this table here the orange is confirmatory factor analysis. Now in exploratory factor analysis, there are different kinds of analyses that can be done. The first one is called principal factor or principal axis. This, instead of using the covariance matrix, it uses the correlation matrix with estimates of the communalities on the diagonal instead of ones on the diagonal like principal components analysis has. It's often we often use squared multiple correlations or SMCs on the diagonal. This also uses shared variance of observed variables, and we call this common factors. And the observed variables are driven by latent variables. Now, I'll talk more about that in a second, but I want to get this idea of common factors. This is the idea that we're searching for underlying latent variables. The search for common factors is focused upon finding those properties that are common to several, many, or sometimes all of the observed variables. And I will better demonstrate with a diagram in just a moment. Now, iterated principal factor, which is what I use most and what I've done in my research most in Stata, is the same as principal axis but uses an iterative process of estimating communalities. Maximum likelihood, or MLFA, is another common factor model. It explains as much variance as possible in the population correlation matrix as inferred from the sample correlation matrix. Here the correlation matrix must be full of rank or non-singular, and it assumes multivariate normality, and that's really important. And it's best applied in CFA, as I'll get to in a moment. The next one is alpha. This is another common factor model, the psychometric method used to find uncorrelated common factors that have maximum generalizability, and it gives reliability estimates for each of the factors. Unlike maximum likelihood factor analysis, there's no distributional assumptions. Now, those four that I just went over are part of exploratory factor analysis. Confirmatory factor analysis is a little bit different. This is theory-driven instead of data-driven. And it's where the researcher defines beforehand the relationship between the variables and tests the model. In effect, the researcher is imposing his or her model onto the data instead of getting a model from, deriving a model from the data. This is another common factor model, and you're able to use maximum likelihood with this one. Now let's go down to this orange table here at the bottom and compare PCA, principal components analysis, with common factors, which includes both exploratory factor analysis and confirmatory. So everything in yellow and orange is considered under common factors. Now PCA empirically has real factors. They're linear combinations of observed variables. Whereas common factors, there's theoretical or hypothetical, which we call latent factors, estimated using a multiple of methods with uniqueness removed. PCA, the factor loadings are literally the correlation coefficients between observed variables and factors, and that makes it easy to interpret. and is quite handy in that way, whereas common factors, factor score estimations are a little bit more complicated. Now I've jumped here to page 8 of your text. This is in chapter 1, and you may have read this and come across it. I think these diagrams help me to better understand the difference between principal components and then the other kinds of factor analyses. Notice here with principal components we have observations x1, x2, x3, and x4. And those observations are what drive these, you can call these latent factors if you wanted. Or as I just stated, linear combinations of the factors, or empirically real factors here. Whereas with factor analysis, we have the observations that are driven by these latent factors, these theoretical or hypothetical factors. Now, the lines here on principal components, they will have values, and these values on them are the correlation coefficients, and easy to interpret. A little bit different with factor analysis. But this is the way I like to think of it. Just notice the direction of the arrows. In this case, in factor analysis, the latent variables are driving the responses. Whereas with principal components, we're getting a summary there. So graphically, they're a little different. Factor analysis, you can tell, will use that common factors, searching for something common among those observed variables to find underlying latent variables. So that's an overview of the different kinds of factor analysis models that there are that are described in your text.